All right, let's start going through this. So let's break out the information that the question gives us. It's a 5 horsepower, 480 volt, 3-phase motor. It's marked with a temperature rise of 30 degrees Celsius, and on the nameplate it has a full load current of 8 amps. So we're going to size our branch circuit first, and here's where a lot of people get screwed up. Ignore this nameplate amperage value for now. It has nothing to do with your branch circuit or your overcurrent protection device. Do not use this nameplate value for your branch circuit or the overcurrent protection device of the branch circuit. We're going to go to table 430.250 in the NEC and find our motor. So it's a 5 horsepower, 480 volt motor, 7.6 amps. And you might be saying, yeah, but this says 460, not 480. Well, you can read in 430.250. Pause and read that. I'm not going to read it for you of why we're using this value. So 7.6 amps. And we're going to take that value, multiply that by 125% because it's a continuous duty motor. And it comes out to 9.5 amps. We need a wire that is big enough to carry 9.5 amps. And because you're cool and you like to support the channel, you pull out your little cheat sheet card that you bought for me, and we're looking for our copper conductor, so you look for THWN 75 degree column, and we're looking for something big enough for that 9.5 amps, which is going to be 14 gauge. Or you go to table 310.16 in the NEC, here's our copper conductors, here's THWN, there's that 20 amps, number 14. So for our branch circuit conductor size, this 14 is going to be plenty because we only need it to carry 9.5 amps. It's good for 20 amps. So we got our wire figured out already. Now let's find our overcurrent protection. We're going to go to table 430.52C1 in the NEC. We're using a 3-phase motor, so it's going to be an AC polyphase motor. And the question said that we're using an inverse time breaker. So here's our inverse time breaker for our polyphase motor, and it's 250% of the full load current. Remember, we got our amperage value from table 430.250. We're ignoring this nameplate value for now, so it's 250% of what we found in table 430.250, so it comes out to 19 amps. They do not make a 19 amp circuit breaker, so we're in 430.52C1A, where the values determined by table 430.52C1 do not correspond to the standard amperage values. You can go to the next higher standard rating. I'm not going to get into all these. This is just a general brief overview on how to size motors. Table 240.6A is just standard amp ratings for fuses and breakers, and we're going to that next size up from 19 amps since they don't make a 19 amp breaker, which is going to be 20 amps. Now you might be saying, well, we can't use a 20 amp breaker on 14 gauge wire, and then I would say read 240.4G, which is going to point you to table 240.4G, which says we can. So we've got our branch circuit figured out. Here's our wire size. Here's our breaker. Now we need to find our overloads, and this is where you do use the nameplate of the motor for the overloads. We're going to look at 430.32A1 for continuous duty motors. We're over 1 horsepower, and it's a separate overload device. It's marked for 30 degrees Celsius, which is less than 40, so it's going to be 125%. For your overloads, you do use the motor's nameplate value, so that 8 amps times 125%, and it comes out to 10 amps. Now, that is what it is. You don't round up, you don't round down. So it would be 14 gauge on a 20 amp breaker using 10 amp overloads. Now, I teach the NEC. I show you the code articles. I show you how to do these calculations and how to figure this out. I don't care if you don't think you should use a 20 amp breaker on 14 gauge wire. And neither does your journeyman or master tests.